Welcome back to the Deep Dive. We're tackling a fascinating piece of research today, looking at a new angle on how we fine-tune those powerful large language models.
Yeah, especially for tricky stuff like mathematical reasoning.
So we've pulled together the key information from a specific research paper for you.
And our mission, really, is to unpack the core ideas, the methods they used, and the findings about this technique they call reinforcement learning via self-confidence.
Or RLSC for short.
Right, RLSC.
And this is important because, while LLMs can show some really impressive reasoning ability, that post-training phase,
That fine-tuning after the main training.
that's crucial for really aligning their behavior, making them better at specific skills or, hitting particular goals.
And that post-training often involves reinforcement learning. But as this paper points out, the existing RL methods for LLMs, like RLHF,
Reinforcement learning from human feedback.
yeah, that one, or even newer ones like TTRL, they often come with some pretty significant limitations. Costs, really.
Okay, let's really dig into that. What kind of limitations are we talking about here, according to this research? Why are things challenging now?
Well, the paper highlights a couple of big hurdles. With RLHF, the main bottleneck is needing all that expensive human annotation.
Right, humans providing labels, ranking output.
Exactly. Or training separate reward models to guide the LLM. That human effort, it just doesn't scale well. It gets very costly.
Yeah, getting good human feedback consistently is a major operational challenge. What about TTRL? Test time reinforcement learning. The paper mentioned that one too.
TTRL is different. It doesn't need human labels right in the training loop itself. It sort of generates its own pseudo-labels.
How does it do that?
Often by having the model spit out many, many responses to a question, and then using majority voting, picking the most common answer as the correct one to learn from.
Okay. But what's the catch?
Well, the paper notes that this approach, it needs a really large number of samples per question to make that vote reliable. They mention using like 64 responses in their comparison study.
64 responses per question. That sounds computationally heavy.
It is. Generating all those possibilities for every single training example leads to high computational overhead, a different kind of cost.
So you've got expensive human labor on one side with RLHF, or expensive computation generating tons of samples with TTRL on the other.
That's the trade-off they're highlighting.
And this paper proposes RLSC as a way to potentially sidestep these problems. What's the big idea behind reinforcement learning via self-confidence?
The core concept presented in the research is actually, well, pretty elegant in its simplicity. Instead of looking outside the model for that reward signal,
Like human preferences or a separate reward model.
right, or even external data, RLSC uses the model's own confidence in its output as the signal to guide the training.
Its own confidence. So the model itself is providing the feedback, almost like it's its own teacher.
That's a good way to put it. The paper frames it as a method that, eliminates the need for external supervision, human labels, those separate preference models, or any manual reward shaping.
The whole feedback loop comes from inside the model.
Exactly. Derived entirely internally from the model's own state, specifically its output probabilities.
Okay, but how does that work mechanically? How do you take something like self-confidence and turn it into, a loss function for a neural network? That feels like the key innovation here.
It is, and this is where the technical depth of the paper really shows. They start by looking at methods like TTRL's majority voting.
Okay.
And they observe that when you pick the most frequent answer from many samples, what you're implicitly doing is optimizing for the mode of the model's output distribution.
The mode, meaning the most probable outcome.
Yes, trying to pile up the probability mass on that single most likely outcome.
So TTRL is kind of indirectly pushing the model towards being more certain about one answer.
Correct. And RLSC makes that explicit. It formalizes that intuition directly. The paper introduces a specific objective function. They call it FPA.
FPL.
Right. Mathematically, it's the sum of the squares of the probabilities of all possible outputs y for a given input x. So FP equals the sum over all y of pyx squared.
Summing the squares of the probabilities. Why the square? What does that do?
Well, think about squaring numbers between 0 and 1. Small probabilities get much smaller when squared.
Yeah, 0.1 squared is 0.01.
Exactly. But probabilities closer to 1 stay relatively large. So if your model's output distribution is spread out, lots of answers with Low probability summing the squares gives you a pretty small number.
Okay.
But if the distribution is sharply peaked, one answer has a high probability, say near 1, and everything else is near 0 squaring, makes those tiny probabilities even tinier. The term for the high probability answer just dominates the sum.
Ah, I see. So maximizing that sum, F, forces the model to concentrate its probability on one output.
Precisely. It rewards distributions that are sharply peaked, penalizing spread or uncertainty. That sharp peak is what the paper defines and formalizes as high self-confidence.
Makes sense. It's a mathematical way to define confidence as certainty in one answer.
Yes. And the training objective then just becomes maximizing this F function.
And how does maximizing that function translate into a specific training loss that you can actually use?
So they derive a loss function from this objective. The main one they talk about is L1. And what it effectively does is train the model to increase the log probabilities
Oh, the probabilities, okay.
of the responses that the previous version of the model was already more confident about.
Why log probabilities?
Yeah.
And why the previous version's confidence?
Using log probs is pretty standard in training these kinds of models. It relates to cross-entropy and just works well for optimization. And using the previous step's confidence, that's the bootstrapping part.
Bootstrapping.
Yeah, the self-supervision aspect. The model uses its current belief state, its confidence distribution from the last step, to decide how to update itself the next step. It reinforces its own strongest beliefs.
So it's sort of pulling itself up by its own bootstraps, iteratively becoming more confident in certain answers.
That's the core mechanism. They also mention a smoothed version, L2, which adds some regularization.
Why smooth it?
Probably to prevent the model from becoming too overconfident too quickly, or maybe getting stuck reinforcing an incorrect answer it happened to be confident about early on. It adds a bit of stability.
Okay, so that's the theory. The mode sharpening objective guides the training using the model's internal confidence. How did they actually test this out? What was the experimental setup like in the paper?
The setup they describe is quite interesting, mainly because it seems so lightweight. They applied this RLSC fine-tuning to the Quinn 2.5 Math 7B model.
Which is already a decent math model to start with, right?
Yes, pre-trained and strong in math.
And the training itself, was it another massive resource-hungry process?
This is where it gets really practical. According to the paper, they trained using only 16 sample completions per question for the RLSC part.
Just 16, compared to the 64 you mentioned for TTRL.
Exactly. Much fewer samples needed. And maybe even more striking, the training duration was incredibly short, just 10 or 20 training steps.
10 or 20 steps on just one data set.
Yep, just on the AIME 2024 training set.
That sounds almost too minimal for fine-tuning an LLM on hard math problems. Did they use any other data or special instructions?
The source is very clear on this. No auxiliary data sets, no extra instruction tuning during this RLSC phase. The signal came purely from applying that RLSC objective to samples generated using the AIME 2024 training data.
Okay, so a very lean setup. Simple, efficient, but did it work? What were the results? Did they see real performance gains?
The quantitative results they show in their table 2 seem pretty compelling, especially given how little training they did. Comparing the RLSC-tuned Quinn model to the baseline version.
The same model before RLSC tuning.
Right. They saw substantial accuracy improvements across a range of math and reasoning benchmarks.
Give us some highlights. What kind of numbers are we talking about?
Okay, so on the AIME 2024 test set, accuracy went up by 13.4 percentage points. That's pretty significant.
13 points, wow.
On Math 500, the gain was even bigger, plus 21.2%. Minerva Math up by 21.7%. Olympiadbench plus 20.8%.
Those are massive jumps, over 20% on several tough benchmarks.
They are. And AMC 23 showed a 9.7% improvement. They also reported gains on GSM 8K and MMLU STEM, which are standard tests too.
And this was all achieved with just, what, 10 or 20 training steps and only 16 samples per question?
Yes, that's the core message they emphasize in the paper. Big performance boosts from a very efficient training recipe.
Any other benchmarks?
They did include GPQA, which is more general reasoning. There, the 7B model saw a smaller gain, about 2.7%. Interestingly, a smaller 1.5B model they tested actually saw a slight decrease on GPQA.
Okay. So maybe more specialized for the math tasks it was trained on.
It seems particularly effective there, yes. The math-focused gains were consistently strong.
Now, beyond the scores, you mentioned the paper discussed an interesting qualitative change. The model started giving shorter answers.
Yes, this was another really interesting finding. The RLSC fine-tuning didn't just boost accuracy, it seemed to change the model's style.
How?
After tuning, the model tended to generate much shorter, more direct answers to the math problems. And crucially, this wasn't because they prompted it differently.
They didn't add be concise or think step by step or anything like that.
Nope. According to the paper, it was an emergent behavior resulting purely from the RLSC training process itself.
So it just learned to be more concise on its own while also getting more accurate.
That's what the qualitative analysis suggests. They included case studies comparing solutions. In one AIM problem example, the baseline model produced this long, rambling derivation with several mistakes, ending up wrong.
Okay.
The RLSC-tuned model for the same problem gave a much shorter answer. It seemed to find a more direct logical path, skipped the bad steps, and got the right solution efficiently.
Interesting.
They saw similar patterns in other cases, like a math problem example, where the tuned model showed better understanding and more streamlined reasoning.
That feels a bit counterintuitive. You might think training for confidence would make it produce longer justifications, trying to prove its point.
Right. But it seems reinforcing the mode, pushing probability onto the single best answer, might implicitly favor the simplest, most direct reasoning path. If that path leads consistently to the answer the model is becoming confident about, it's a fascinating side effect.
It really is. So how does RLSC fit into the bigger picture then? How did the paper compare it to other related work?
Well, they position it relative to methods like RLHF, TTRL, but also others like RLVR, SBC, AZR techniques that might use external tools or self-consistency checks.
And what's the key difference?
The main distinction they draw is that while those other methods often rely on some external signal, human labels, reward models, extra data, large sample sizes, verification tools,
Right, something outside the core model.
RLSC stands out because its entire training signal comes from inside. It's derived purely from the model's own predicted probabilities and how concentrated they are.
Through that mode sharpening idea.
Exactly. It's leveraging the model's internal state, its own evolving beliefs, to improve itself, a form of self-calibration.
Okay, so let's try to wrap this up. To recap this deep dive into the research paper, RLSC, reinforcement learning via self-confidence,
Is presented as this lightweight, zero-label fine-tuning method, no human annotations needed.
and it works by using the model's own internal confidence, formalized through that mode sharpening objective.
Right. Pushing the model's output distribution to get really sharp, focused on a single answer it believes in.
And the results. The paper showed it achieving pretty substantial accuracy gains, especially in math.
Yeah, big jumps despite using minimal training data and compute compared to other methods.
Making it seem like a really practical, efficient approach.
Definitely. The paper kind of pitches it as bridging ideas from ensemble methods like TTRL with principles of self-supervision, using the model itself to guide improvement.
So a final thought for you, our listeners, based on this research. The paper itself notes there's more work to do, like figuring out exactly why that concise reasoning emerges.
And tuning things like the smoothing or sample counts.
But think about this. If just training a model to become more confident in its best guess can lead to better accuracy and simpler reasoning, what does that tell us about how these models actually think or learn?
Could this self-confidence principle be more fundamental? Could it work for tasks way beyond math? Lots to ponder there.
Indeed. Great questions to keep in mind. Thank you for joining us for this deep dive into this fascinating research paper.